this is just a little picture from the university that I'm at, that I come from, La Trobe University. I'm actually visiting Guillermo at the moment at the University of Queensland. Having a very fun time, by the way. So if any of you get an opportunity to visit this campus, it's a really beautiful campus, the University of Queensland, and Brisbane's been a very entertaining place to visit. So this is just a sculpture of Governor La Trobe on his head, but I often use it in talks because I'm used to talking on what's sort of the opposite antipodal point, I guess, of where I live in the Northern Hemisphere, is where I normally give a talk. In this instance, I think it's the other way around. So I'm giving a talk on the right side of the hemisphere, but maybe the antipodal point of time, since I'm a bit of an early person, and this conference pretty much starts about 2 hours after I go to sleep normally and finishes about 2 hours before I finish. So it's sort of like the temporal version of Iceland or something like that for me. Anyway, so apologies if I start rambling or speaking strangely, but it's probably just some REM sleep kicking in during the talk.
Is the statue actually upside down in real life? It's actually upside down?
Yes, it is. Yeah, so it's supposed to be a sculpture. I mean, it's a sculpture that's just like a classic statue, but it's positioned on its head. And actually, the university bought it. It wasn't made for the university. They just purchased it. It's like a sculpture purchase because they thought it was an amusing thing for the university. So, so I'm going to make up my own version of finite model theory, but I believe it's consistent. But some of the motivations are not necessarily going to sit alongside the classical motivations of finite model theory. But I'm going to start with this perhaps vaguely well-known suggestion in Chang and Keisler from the early 70s, which was that model theory is logic plus universal algebra. I actually don't know if this is really very true even in 1973, but there's certainly a big synergy between those areas in the early stages of model theory. And I think perhaps modern model theory has gone off in directions that don't currently overlap so much with universal finite model theory. So
we lost you for a moment there.
Sorry, it says your internet connection is unstable. Sorry. Hopefully that won't happen too often. I was just suggesting there was at least a big synergy, a significant synergy between these areas. However, with finite model theory, I think that perhaps the tools and perspective of finite model theory hasn't really been taken up as model theory was. And so this talk is about that. I'll need to give a bit of a primer. I don't know if you can still hear me, but my video has stopped.
Yeah, we can. Well, you're still coming through mostly clearly, but the video is off for now.
Okay, I'll leave it off for a little bit. So it turned itself off for some reason, presumably because of the quality of the connection in this hotel.
No, sorry, I turned it off, Marcel. I turned it off so the connection is a little bit better.
That's fine, Guillermo. Thank you. It's a good suggestion. So I thought I should give a bit of a universal algebra primer because this isn't really an algebra conference per se. So a basic overview wouldn't hurt. So as you may well know, a big theme in universal algebra is varieties. So this goes back and right to the 1930s with the work of Birkhoff here, and perhaps actually the first preservation theorem that may have been proved, which is the one for equational logic, which says that classes defined by equations, and I mean here universally quantified conjunctions of equalities and atomic sentences, are exactly those that are closed under taking homomorphic images, subalgebras, and direct products. And I've just put this in here. So this turns out to be equivalent to taking homomorphic images of subalgebras of direct products, which was a later observation of Tarski's, but it's just kind of useful. The other thing I thought I should flesh out here is the I guess this is like the first homomorphism theorem, so everyone would have seen this in an undergraduate algebra course, but it's just a sort of a useful thing that we'll have to see a bit later. And this is the idea that homomorphisms that are talked about up here relate to what are known as congruences, which are just equivalence relations that are stable under applications of fundamental operations. So as we probably know, the kernel of a homomorphism is an equivalence relation, certainly, but it's also a congruence in the sense that it's stable under applications of fundamental operations. And if we have a congruence, then the natural map is a homomorphism. So these are sort of two different perspectives. One is sort of like an outward, yeah, and we'll have to flip between them. So that's useful when we come to look at varieties. So if we're going to have a bit of a finite model theoretic investigation in universal algebra, then varieties would be a natural place to start because it has been something of a central backbone of investigation in universal algebra. So if we're going to talk about varieties, then we need to talk about subdirectly irreducibles, because this is a bit like the notion of a prime number. So if we're studying number theory, we obviously need to know about the indecomposable numbers, and the indecomposable algebras are the best candidates for such a thing are the subdirectly irreducibles. And I've given a definition here. What it says is that if we what it means to be subdirectly reducible is that whenever we embed into a direct product, then we should embed into one of the factors. And another alternative definition here would be that, which is equivalent to the previous one, is that if we have a pair of distinct elements, then there is a pair of distinct elements, and every non-trivial congruence will identify that pair of elements. And these two are equivalent. And so this is these are a bit like the prime numbers of the algebra world, the universal algebra world. And part of the reason for this is that we can always decompose an algebra into its subdirectly irreducible quotients. So what we do is we take a pair of elements A and B that are not equal, and we look for a maximal congruence that doesn't identify them. And you can show that such things exist using Zorn's lemma, but in a finite algebra, you don't even need Zorn's lemma. And you'll find that the corresponding quotient has this property. So it turns out, and this is in Birkhoff's original paper, that every algebra embeds into a direct product of its subdirectly reducible quotients. This talk won't be quite as heavily algebraic, but I just thought I should cover some or revisit a couple of these notions to start with. So perhaps I should mention then, if we're interested in looking at membership in varieties, then we can sort of reduce this to the problem of looking at membership of subdirectly reducibles, because this little lemma here tells me that an algebra A lies in a variety if and only if all of its subdirectly irreducible quotients do. And this is just because the subdirectly irreducible quotients are homomorphic images. So if A is in the variety and the variety is closed under taking homomorphisms, then so will these be in the variety. If all the subdirectly irreducible algebras quotients are in there, then A will be in there as well. So a few classical problems in universal algebra, and I've just selected the ones that I think are perhaps the foremost problems. These are not necessarily open problems. Some of these have been resolved, as you'll see, but these are ones that I think were a big driving force in universal algebra throughout the history. So this one here is Tarski's finite basis problem, which was perhaps the foremost problem of all, which was just the question of whether or not there was an algorithm to determine if a finite algebra had a finite equational basis. So if its variety was finitely based, we would often say. And you may or may not know that this was eventually solved by Ralph Mackenzie in a really groundbreaking and very difficult series of papers. So, actually, it wasn't really made humanly understandable until a bit later in the 1990s, when the final stage was simplified a lot by Ross Willard, although Ross's paper is also quite difficult, but it's just a lot simpler than Ralph's original final stages. The Quackenbush problem, I believe it was called, asks if we have a finite algebra, and is it true that the variety either has only finitely many subdirectly reducible members, in which case they would all be finite as well, or alternatively, there's no cardinal bound on the size of the subdirectly reducible members. And this was also solved negatively by Ralph as part of a step towards his resolution of Tarski's finite basis problem. The Parkinson problem. So this is the question which I think is perhaps the foremost unsolved problem, at least in my view, which is the one that asks if there are only finitely many subdirectly reducibles in the variety, that we already know that they must all be finite in this case through some theory, then is it the case that we have a finite equational basis? So this has been resolved for almost any manageable class of algebras, but it's unresolved in general. And a natural variant might be to replace finitely many subdirectly reducibles with perhaps the property that the subdirectly reducibles themselves are a finitely axiomatized class in first-order logic. And the final problem I have here is the Eilenberg-Suchner-Berger problem, which is the first of these problems that I think itself probably does genuinely satisfy the condition of actually being a finite model theory question. It says that if you have a function that amongst finite algebras, the finite part of the variety, which will be the homomorphic images of the subalgebras of finitely direct products of A or finitely direct powers, if that's determined by a finite set of equations amongst finite algebras, is it true that the variety is, in general, is determined by finitely many equations? So I think this is a kind of a genuine finite model theoretic question. And this has been solved positively for semigroups, but remains open in most other classes. There's been a few developments by a couple of other people, but semigroups is the main class where it's been solved positively. And again, it's actually quite difficult to prove this result of Marcus appears. So you'll see in all of those problems, this a real obsession with finite. And some of those problems even perhaps are finite model theoretic in character, but I think a lot of these questions actually are quite interesting if they were to be reconsidered in a sort of a finite model theory perspective. So this is not asking for any particular motivation from computer science, although a big theme that emerged, of course, in more recent times in universal algebra has been computational complexity considerations. And once we start to look at them, then all of those problems do become a lot more interesting, and the finite model theory becomes a bit more relevant, I think. So I wanted to give an overview of two major parts of universal algebra that are, I think, finite model theoretic in character. I can't really give a fair go to Tame congruence theory. I'm not a true expert in Tame congruence theory, to be honest, and it is a moderately difficult little topic, but I'll just give a bit of an overview and you'll see it really is kind of an interesting little investigation into finite algebras. From everything's finite here. I think it sort of really does satisfy the conditions to me. So the first idea is the idea of a minimal algebra, which is supposed to be some finite non-trivial algebra. So non-trivial meaning just not more than one element. And it has the property that every unary polynomial is either constant or a permutation. What's a polynomial mean? It's just a term, except you're allowed to make. And it turns out that if under this definition, that it turns out that for finite algebras, there's very few actual possibilities. You get the two-element cases. You get some situations that are essentially unary. So that means that all possible polynomials are really just projections onto the unary ones, or they turn out to be equivalent to a vector space over a finite field. And so if one pushes on a little bit further, these can be classified into 5 types. But basically, you get a group action type with the property that all polynomials are effectively just unary polynomials that and they form a group action, so like a unary algebra. You get the semilattice types, so you're polynomially equivalent to a semilattice or a lattice or a vector space, as we just saw here, or to Boolean algebra. And so the Tame congruence theory comes in recognizing the fact that if we look at an algebra, we look at its lattice of congruences, because they do form a lattice, then the covering pairs there correspond to simple algebras, and within simple algebras in the variety of A, within simple algebras, we can find sort of little shadows of minimal algebras, and we can look at what possible types there are. And the important fact is that the properties of varieties turn out to be determined by, or often determined by which combinations of these 5 types are emitted. And a really good example of this, which I think reinforces the finite model theory aspect here, has come out from the modern development of polymorphism algebras in the study of finite template constraint satisfaction problems. So I won't say what a polymorphism is, but it's basically like an n-ary endomorphism. And you look at the algebra of all such high dimensional endomorphisms, and you look at, it turns out that emitting various combination of types in the variety of that algebra corresponds to solvability of the constraint satisfaction problem by various different algorithms or at certain levels of complexity. The most famous of which is the really amazing Budatov-Zhuk theorem from about 2017, that a finite template CSP is solvable in polynomial time if the group action type is emitted in the variety of the polymorphism algebra, and otherwise it's NP complete. So this is a sort of an interesting universal algebraic version of finite sort of contribution to finite model theory. Another one is pseudovarieties, which is perhaps more semigroup theory than universal algebra, but I'll skip through to this original result of Marcel, Paul, Schutz, and Berger, which is that the variety of star-free languages, which is some just star-free regular languages, is somehow equivalent to the class of finite aperiodic semigroups. And the connection is you look at the transition monoid, or in fact, the syntactic monoid of the language, excuse me, and it has to be aperiodic, meaning all subgroups are trivial, and one can sort of go the other way. Someone gets a lattice of varieties of regular languages, and they're duly isomorphic to the lattice of pseudo-varieties of finite semigroups. And pseudo-varieties are just like the finite version, but we only look at finitary direct products. And because of this, it's not necessarily the case that they are defined by equations. And in fact, what happened in the world of semigroup theory was that they invented sort of a topological approach, because it turned out you could describe these by limits of equations. And a nice way to think about this is if you take something like a free semigroup, you can put a metric on that semigroup, which determines distance between 2 words according to the size of the semigroup that distinguishes them. You can take the completion of that and you end up with a Boolean topological algebra. And then instead of equalities between elements of free algebras, which is what an equation might be, you end up with equalities between elements of these free pro-finite algebras. And that's what ends up being sort of like a language for describing pseudo-varieties. So this is an interesting sort of infinitary approach to studying what is effectively a kind of a finite model theoretic problem. So let's revisit all those.
Sorry, just want to let you know, Marcel, you've got about 10 minutes.
Oh, brilliant. Thank you, James. So let's just revisit those classical problems and just have a go at making up, without any particular motivation other than the fact that it's in the spirit of the exercise, what they might mean if we were to try and make sort of finite model theoretic versions. So perhaps this might be a version here. Is there an algebra that can be finitely axiomatized as to what this should mean? Because maybe at this level, Birkhoff's theorem doesn't hold. Actually, it clearly doesn't hold. It's very easy to show it doesn't hold for pseudo-varieties in general, but it's not much less clear whether it holds for pseudo-varieties that are generated by a single finite algebra. So should we be talking about pseudo-equations, first-order logic? Is there a sort of a pseudo first-order logic? Some sort of hybrid? I don't know, actually. It's a good question. The Park-Jorgensen problem. I'm going to skip over the Quackenbush one. I think there is a nice finite model theoretic version of that, which might relate to the spectra of subdirectly reducibles, but I'll miss that one out. Park-Jorgensen problem. Maybe we could talk about first order axiomatizability of subdirectly reducibles. Does this imply a finite identity basis for the finite part of the variety or something like that? And the last one would be first order Heidenberg-Schützenberger problem, which would be something along the lines of, if the finite part of the variety is first order definable, does that imply that the variety is first order definable? And I would argue that perhaps Heidenberg and Schützenberger should have really stated this version of the problem And the only reason to put equations here is perhaps because one might have assumed that something like Birkhoff's theorem would be the only way that you could ever think of describing such a class. I'm not quite sure. Anyway, that's that. So if we wanted to get a bit more sort of computer science style motivation, or at least the kind of motivation that might have existed in the development of some facets of finite model theory, we could look at some complexity theoretic considerations, because there's been considerable effort in understanding the computational complexity of this problem, which I'm calling var-mem, which is just deciding membership of finite algebras in this variety. And so, for example, the first order Eilenberg-Schütz-Berger problem is just the question of whether or not the first order definability of this problem is equivalent to the finite basis property, which seems now to be quite a natural question to be asking. So we're going to see, actually, if there is a main result in this talk, it's that the answer to this is that it is not equivalent. There is a counterexample to the first order Eilenberg-Schütz-Berger problem. It's actually a sort of an oldish result. I just haven't actually published this fact, but it really stems from this interesting observation or result from 2008. This is again more about Boolean topological structures, so infinite structures, but they're somewhat similar to finite structures, and you quickly get this little interesting fact here, that there is a finite lattice L for which the finite part of its quasi-variety, I didn't mention quasi-varieties before, but they are just the same kind of thing, but without the H. So the quasi-variety at the finite level is axiomatized by a single first-order sentence amongst finite structures. But what you should have expected was universal Horn sentences were the correct syntax here, but in fact, no finite set of universal Horn sentences work. So universal Horn sentences are what would characterize the quasi-variety if we didn't have the finite part. And actually, in the relational signatures, this is actually an open problem due in part to the previous speaker from 1997, and that seems to remain open. But the algebraic version turns out not to hold. And some other interesting ones here, this is something that sort of like followed on from that, which due to Lucy Ham, which is for any lattice, if we work in the world of bounded lattices, we'll look now at it's a bit like the CSP for L, if you like. So it's looking at the problem of taking a bounded lattice and asking, does it have a homomorphism into L? Then it turns out that this class is always first order definable, but it isn't definable by universal sentences. And again, the correct syntax here should have been something like a universal strict Horn sentence or something like that if we were going to use classical model theory. So here we get a sort of a failure of something like, well, I guess the Washtarsky theorem at the finite level for here, but also for things like an anti-variety version. And in fact, she was able to push on and show that that the opposite held in relational signatures. So this is effectively Benjamin Rossman's homomorphism preservation theorem. The only difference here was it's a bit weaker than that because it's only working over structures mapping into a fixed finite structure, but also it has the additional fact that it's restricted to classes that are defined in similar ways to K. So K here, of course, is a variety, so it's defined by university quantified atomic sentences. And so this is just a proof of something like a restricted homomorphism preservation theorem, restricted to classes of defined in that way. And it turns out this does hold in the relational signature, but fails in algebraic signature. So this really does suggest that algebraic objects are going to behave quite differently, which maybe could be expected, but these are the only instances I know of. So maybe in the dying moments, I'll just give a bit of a sketch. So the idea of this result here, which is that there is a finite algebra A whose for which the finite part of its variety is definable by a sentence that has for all there exists for all, but it can't be defined by any for all there exists sentence, and nor by any system of pseudo equations. It's a bit harder to see this because actually it's an easy result, this particular feature, but it doesn't follow quite so simply because pseudo equations, as mentioned, are really about limits of equations, so they don't really fit into first order logic themselves. So the variety itself, though, if we didn't have the finite restriction, is not first order definable. Oops. So here we have that problem I mentioned before, which is the question about whether or not the SP preservation theorem works at the finite level, which remains open in the relational signature, which is probably, I think, what Adachina and Gurevich were looking at. Here is Belkin's lattice, M33, and it turns out this has no finite basis for its quasi-equations or universal Horn sentences. It's pretty easy to show that at the finite level, it still doesn't have a finite basis in universal Horn sentences, but it is first order definable amongst finite algebras. And because I won't have much time, I'll just explain that the fundamental idea here is that when we look in this class here, the way we need to decide membership is in terms of finding quotients of algebras. So an algebra is in this class if for every pair of elements there is a quotient that separates those two elements, and likely many subalgebras of that lattice, it's only this big. And the critical thing is that congruences, each congruence class on a finite lattice is an interval in a lattice. And intervals in lattices can be defined in terms of there exists a top and a bottom, and the elements are just the things that are ordered in between. And this enables you to actually talk about the nature of a congruence of the quotient, by just existentially quantifying elements. So I'll probably stop there. So I won't have time to explain how to push on to the variety version, but this involves observing a new idea of, I guess, first order definability of the subdirect decomposition process. And that enables you then to have a different algebra that's sort of like an enrichment of this one. It also has some extra elements. And then you need to talk about decomposition by way of this first order formulas into things that look a bit like these. But I'll have to stop there, I think, because I've run out of time.